Okay, so without further ado, let me hand it over to Dr. Gonzalez.
Okay, thanks for that intro, David. So let me go ahead and start sharing my screen. Everybody see that okay?
Yes.
Good.
Yeah.
All right. So as David said, this talk will be based on a book I co-wrote with Jay Richards titled The Privileged Planet, How Our Place in the Cosmos is Designed for Discovery, back in 2004. And by the way, just before the book was published, a few years before, I wrote somebody has something.
Okay, can someone, can everybody mute their audio, please?
Okay.
Thank you.
The connection with Hugh Ross, I wrote a few articles for his magazine they used to publish called, what was it? Facts and Faith, I believe it was called. Like it was about 20 years ago, and I wrote a short article on an aspect of this, of what I'll be presenting today. So I'll start with an illustration that may seem odd. Consider, but just bear with me. Consider that you live in this tiny room, what looks like a jail cell. It's got what you need to live. It's got but it's locked, and you're fed food and water through a small slot in the door every day, just bare necessities. And you got a cot to sleep in, and toilet, etc. There's a tiny window that lets in some light, but otherwise you can't really see any detail outside. And you spend your existence like this. We might call this a room without a view. And if you were born into this situation, born in this place, you might think, well, why should I expect anything more than this? After all, I am provided everything that I need to exist, to live. Suppose you're upgraded one day to a slightly better room with a slightly better view. Here you can actually start to see some details outside, but it's the same view every day, and still can't get much of a view of the world outside your cell. Well, compare these to, say, somebody living in this place. Wow, now there's a view. There's a room with a view. And you might start to say, what did I do to deserve this? This is a little bit more than what I really need for everyday living, complete with champagne and comfort, or something like this. Say maybe on a Caribbean island or something. Now let's consider our situation somewhat. Let's consider our view, say, of the night sky. Now, I'm sure, well, living in LA now, it's hard to get this kind of view, but I'm sure all of you at some point in your lives have gone out to a dark site and looked up at the night sky and been enthralled by the beauty of the night sky. And it's all the stars you can see in a really dark sky, away from city lights on a moonless night. That's a view. And some of you might have wondered, wow, that's a lot more than I need just for living. Seeing the stars so clearly, so many stars at night. What did I do to deserve this? You may wonder. We could easily have been in a different situation. Today we know about all the other planets in the solar system, their atmospheres, and even what it would look like from their surfaces. Our atmosphere could have been a bit thicker, giving us maybe very blurry visions like I've shown here on the right side of my screen, maybe seeing some light from distant sources, but nothing clear, everything blurry. Or perhaps it could have been a completely overcast sky. We would have been treated to something like this every night. A sky that's translucent. It lets, say, sunlight filter through, but otherwise you couldn't see anything. You couldn't see the distant stars at all. No, instead, not only can we see many stars with our unaided eyes, but even with just modest optical aid with a small telescope, for example, a pair of binoculars, we can see that there's a lot more detail in there. So here's a picture of the Lagoon and Triffid nebulae for those of you who maybe amateur astronomers or have a small telescope. You can see these with a small telescope, and it's quite surprising that there's so much richness of detail in the night sky. It's not just that, okay, we can see the stars, but if you look through a telescope, things just look blurry and bigger but blurrier. You don't really see any more detail. No, it's not like that. With a very small optical aid, modest optical aid, you can see much, much more. There's a richness of information in the night sky. And so here's a picture of the Orion Nebula. So you might say we live in a room with a view of the universe around us. And you may begin to wonder, wow, this is kind of an odd situation. You know, why should I be able to see all this? I don't need all this for my everyday existence, for living every day. So the first point I want to make is, well, first of all, ask the question, why can we see the stars? I think that's a profound question. And I don't mean it in the sense that some people may ask a scientific question like, why is it the case that we can see the stars? What has to be true? Okay, we have to have a transparent atmosphere. We have to have eyes that are sensitive enough. We have to have stars that are close enough and bright enough for us to see them. That's the scientific answer to that question. I mean the deeper metaphysical answer to this question. Why can we see the stars? And so I want you to keep that question in the back of your mind as I'm going through the presentation tonight. So the first point I want to make is there's much more information there in the starry realm that than we can see with the unaided vision. It doesn't take much optical aid to see much more deeply, much more. There's just, it's like a picture that you keep zooming into that never ends, seemingly. So our intuition tells us that this is a strange and wondrous situation that we should be privy to all this. So we should be able to see the stars and nebulae and galaxies, star clusters, planets, etc. So here's a quote from Hans Blumenberg, a German historian that who put it very poetically, I thought. The combined circumstance that we live on Earth and are able to see the stars, that the conditions necessary for life do not exclude those necessary for vision, and vice versa, is a remarkably improbable one. This is because the medium in which we live is, on the one hand, just thick enough to be able to enable us to breathe and to prevent us from being burned up by cosmic rays, while on the other hand, it is not so opaque as to absorb entirely the light of the stars and block any view of the universe. What a fragile balance between the indispensable and the sublime. So the indispensable meaning we need an atmosphere to breathe, to live, and the sublime, our view of the distant universe, something we really don't need. So why is it that there's this situation, this set up the way it is, that we can see the stars? So that is background. I want you to keep that now in the back of your mind. And I'm going to now start talking about the thesis of our book, The Privileged Planet. And to understand that, we have to talk about habitability, first of all. So there's a chapter in the book on the necessary conditions for life at the most basic level, at the level of chemistry. And now, Earth-based life is the only life that, of course, that we have experience with. And Earth-based life is universally based on two things in particular that are true for any life on Earth. First of all, is carbon is the building block for all life, for the molecules of life. And then water is the medium, universal medium in which those biochemical reactions take place. Well, there are good reasons for that. There's good reasons why life is based on carbon, first of all. It has an ability to form large metastable molecules, better than any other element, and to bond with many other elements with similar affinity. So it can make a great diversity of chemical compounds that are stable, but not so stable that it takes a great deal of energy to break bonds. So, for example, it's not like silicon oxide, say it's like sand. Those are very strong bonds, and those bonds are so strong that you have this practically inert compound. But carbon can form bonds with hydrogen and oxygen and nitrogen and many other elements. And the bonds are comparable in strength to each other. So it has similar affinity to these many other atoms that can form a great diversity of bonds. And it can form very long chain molecules. Now, why is that important? That's important because then it can, information can be encoded in these very, very large molecules, so DNA and RNA. And so that's a basic requirement for life, that you be able to encode the instructions for making a copy of the organism in a substrate sufficiently large that it can hold all that information. And really, carbon is the only one that seems to be capable of doing that. There are far more organic compounds, for example, than there are compounds made of any other atom. And the number keeps growing every day. And then water is the universal medium of life. It has a number of properties, anomalous properties, they're called, that are really important for life. Just for starters, it's liquid over the range of temperatures at which carbon chemistry is most active. It has almost nearly extreme values on a number of its properties, like the specific heat of vaporization. It's one of the highest of any element or compound known. It's got a high surface tension. It's highly anomalous in that its solid state floats in the liquid state. In other words, the solid state of water is less dense than the liquid state. There are very few other substances in the universe that do that. And those properties are important for life at the cellular or the organismal level, or even at the planetary level. Now, to build life, you need not only carbon and hydrogen and oxygen, the constituents of carbon and water, but you need a number of other elements. For bacterium, for example, you need 17 essential elements. Those are marked in dark, the dark squares here in this periodic table of life. And then for complex life, mammals and us and reptiles and so on, you need to add another 10 or so. So roughly 27 essential elements for complex life. So you're talking about a pretty big chunk of the first half of the periodic table, all the way up to iodine, the heaviest one. That's essential for complex life. So you need to have these elements in the right relative abundances, in the right chemical forms to be useful to life, and of course accessible to the life. They can't just be, say, sequestered in the center of a planet where they can't be reached. They've got to be wherever the life is. In the case of Earth, it's in the crust of the Earth. And you can't have too much of some of these, because too much of some of these are going to be too toxic then. And not enough of some of the essential elements, and then you're not going to have life, because they are essential elements in certain minimum concentrations. So there's a lot more I could say here, but this is just you might say almost an outline form. There's so much research being done in astronomy today on the question of habitability. What makes a planet habitable? In fact, the whole area of astrobiology really exploded starting in 1995 and 1996. 1995 with the discovery of the first exoplanet around another sun-like star. In fact, it was October of 1995 when it was announced that a planet was orbiting 51 Pegasi. And then less than a year later, summer of 96, was the announcement of evidence for life in an ancient Martian meteorite, ALH 84001. If any of you remember that, old enough to remember that controversy, that evidence hasn't really survived scrutiny over the years. But nevertheless, those two events did launch the modern era of astrobiology research, and a lot of scientists have switched their specialties over to this area. I was one of them who was already interested in this question prior to 1996. In fact, in the early 90s, I was interested in the question of astrobiology, coming to it from perspective of an observational astronomer. So for the purposes of our discussion, I'm going to define a habitable planet as a terrestrial planet that supports complex carbon and water-based life. These chemical necessities for life put strict constraints on what kind of planetary environment you need, right? So you need a planet that's going to have at least some liquid water on it. It's going to have carbon in the right chemical forms, and then all these other required elements. Depending on the life form, then it will determine exactly how many of those essential elements you need. But we're going to talk about complex life, complex carbon and water-based life. The planet needs to exist in the circumstellar habitable zone. So that's a region around the host star where the planet can maintain liquid water on the surface, for at least parts of the surface. And the planetary system needs to reside within the galactic habitable zone. So now we're talking about the size scale of the entire galaxy, the Milky Way galaxy, about 100,000 light years across. And there are regions of habitability within the Milky Way galaxy, similar to the regions of habitability around a star. I'll have more to say about the galactic habitable zone later. And then during the cosmic habitable age, this is a newer idea. And this is the recognition that basically the whole cosmos is changing over time. The star formation rate in galaxies, for example, is changing over time. It's at the present time, it's declining overall. Early on, it was stars were forming at a much higher rate. There were more supernovae going off, etc. The universe is, you might say, winding down, and the rate at which stars are forming is slowing down as it continues to expand. So here are just some of the things you need for a habitable planet, and this is not a complete list. It's just a kind of a highlight, an outline form of some of the broad categories. So you need the right kind of terrestrial planet, having the right size, the right composition, the right kind of atmosphere. You need a stabilizing moon for a planet like Earth. It helps to stabilize the tilt of its rotation axis. Not only that, but it aids in producing the tides, which wash nutrients from the continents to the oceans, and therefore which provide the life in the oceans with nutrients that they need to have a very active biosphere and the oceans. You need plate tectonics, the cycling of the crust through the mantle, and the elements that are also riding along with it, in particular carbon. It's part of the carbon cycle over a long period of time. You need the right composition atmosphere, the right thickness atmosphere. Can't be too thin like Mars's atmosphere. Can't be mostly carbon dioxide. For complex life, you need a substantial fraction of oxygen in the atmosphere. You need the right kind of planetary neighbors. You can't have giant planets that are too many or too close to your terrestrial planet if you want to keep your planet orbiting in a nice circular orbit for a long time. It's better to orbit a single star than in a binary or multiple star system as far as stability of a planet's orbit, and also you want to keep the planet's orbit circular. There's only a restricted range of binaries that would allow that. So most binary star systems are ruled out. The right kind of galaxy. So a spiral galaxy is best with a flattened disk like ours. the right place in the galaxy. And again, I'll have more to say about that later, so I'm not going to say much about that. Now, I already talked about being in the right cosmic time. And not only that, but you need to be in the right kind of universe, a universe where the physical constants are fine-tuned for life, where things like the charge of the electron, the masses of the fundamental particles, the quarks, and the electrons are all within a narrow range. The expansion rate of the universe, all that, the initial entropy, all has to be fine-tuned for the universe to have any life whatsoever anywhere. So here's a dilemma. With such a large universe that we live in, with something like 10 to the 11th galaxies in the observable universe, each galaxy having something like 10 to the 11th stars on average. There's a lot of planets. Now we know from the research being done with exoplanet discoveries that there are a lot of planets in the solar neighborhood. So you might say there's a lot of rolls of the dice or flips of the coin, if you want to think of that as representing chance. So how do you decide if chance has had enough room to operate in to explain our Earth? Or maybe there's not enough rolls of the dice. Maybe there just aren't enough planets in the universe to explain the fine-tuning, local fine-tuning, even for the Earth. And I just don't, in my opinion, I don't think we know the probabilities well enough yet for the conditions for habitability to say whether or not chance can explain it. So I think we need something else as a tiebreaker. I mean, we may know that probability in the relatively near future because of so much research being done in the area of astrobiology, particular work on exoplanets. So we may know the answer to that soon, one way or the other. But I think there's another way, another tiebreaker. There is a tiebreaker, in my opinion. And that's the evidence that I'm going to be presenting tonight on the privileged planet thesis. Oh, somebody has their TV. Okay.
Yeah.
Somebody had their TV on.
Yeah, can people turn off their mic, please? Mute the mic. Thank you.
Thanks. Okay, so the basic thesis I'll just present to you then is that habitability correlates with measurability. Believe it or not, this was the original idea for the title of the book. My co-author didn't think that was a good idea. I'm glad he prevailed. So we have a much nicer title, The Privileged Planet, much better alliteration anyway. How our place in the cosmos is designed for discovery. And so the idea is it's not just habitability that we consider. It's not just the conditions you need for life, but we also consider something else. It's measurability, or if you will, observability or discoverability, kind of almost synonyms, that these two are linked in some way, that the conditions for life, habitability, those conditions are linked with our ability to measure the world around us and observe it and measure it and discover things. That's the basic thesis. So, or to put it in a short paragraph, the same narrow circumstances that allow us to exist also provide us with the best overall setting for making scientific discoveries. I say overall because you can think perhaps of counterexamples in specific cases. For example, wait a minute, you said the Earth provides us a great view of the distant universe and we can see the stars clearly. Wouldn't you be able to see the stars even more clearly from the moon because it has no atmosphere? And sure, yes, you would. You would be able to see the stars more clearly from the moon. But there are many other ways that being on the moon would hurt you as far as making scientific discoveries. Okay, there are things that are lacking on the moon because it lacks an atmosphere, it lacks a hydrological cycle, it lacks plate tectonics and so on. There are important things that you wouldn't be able to discover because of those things that are absent on the moon that the Earth has. And so it's like designing a laptop. It's you engineers use a phrase called constrained optimization. They optimize each aspect of the laptop, constrained so that that part of the laptop has to be part of the larger design of the laptop, so it fits. So it may not be the best hard disk, for example, that you could ever build, but within the constraints of having the small compact computer with small energy usage and so on, you're constrained with certain parameters for your hard disk that may not make it the best overall hard disk, but within those constraints, it's the best. It's the best hard disk in that setting, and so that's what we mean, that it's the best overall setting for making a wide range of scientific discoveries. The very conditions that make Earth hospitable to intelligent life also make it well suited to viewing and analyzing the universe as a whole. And so here are just some examples of what I call the correlation. Perfect solar eclipses, layering processes on the Earth. By that I mean things like deposits on lakes, lake sediments, ocean floors, growth rings on trees, and stalactites, stalagmites, and caves, or living things that produce growth rings, as well as trees, maybe corals, mollusks. So layering processes are things that you might say have time-stamped and time-ordered recordings of the environment that you can then recover. They're kind of archives. That's a whole field called paleoclimatology that make use of layering processes to reconstruct the ancient climate of the Earth. The Earth has many of these kinds of things. Plate tectonics, it's the cycling of the crust down and deeper into the Earth, and then the constituents of that crust are recycled back up to the surface, and you need that recycling for life, but also that recycling helps with measuring the Earth's interior. The transparency of the atmosphere, again, I talked about that one at length. Planetary neighbors, the fact that we have multiple, 8 planets in the solar system. You may be surprised to learn that the particular architecture of our solar system was very important in scientific advancement, in particular in advancements in the learning about the nature of gravity. That we live in a rich planetary system has been very helpful to science. Stars, we orbit a star, and we can see many stars around us, and we can learn a great deal about them. In fact, they're very information rich, surprisingly so. Our place in the galaxy, I'll have more to say about that later, so I'm not going to say much now. Our place in cosmic time, the fact that we can do cosmology is actually very much dependent on the fact that we're living in a particular point in cosmic time. In fact, it's probably better to do cosmology right now than it is in any other time in the history of the universe, either past or future. And we lived in a fine-tuned cosmos, one that's fine-tuned not only for life, but fine-tuned for being able to discover its properties. So I'm only going to cover a couple of these in some detail tonight, just to give you 2 examples. Each of these forms a separate chapter in the book. The first one, Perfect Solar Eclipses, is the first chapter of the book. And the reason that is the first one is because that was the first example I thought of, I discovered after I went to see a total eclipse in India in 1995. I really began thinking about them and the particular circumstances for eclipses on Earth. And then I discovered that there's this remarkable link between our ability to see total eclipses and our existence on Earth. And so I'll discuss that in some detail. So I don't know how many of you went to see that eclipse through the United States in 2017, but I got to see that. I was in the path of totality. I saw that in Missouri. That was my second total eclipse. First one, as I mentioned, was from India in 1995, and that was what led me to start thinking about eclipses in more detail. I wrote a scientific paper in the journal Astronomy and Geophysics in 1999, where I talked about this interesting relationship between the observability of total solar eclipses and our existence as observers on Earth. So let me just give you some background Astro 101 on what you need to produce a total eclipse. Well, you need a luminous body, in our case, the sun, an eclipsing body, in our case, the moon, an observer platform, the surface of the Earth, and they have to be the right distances apart and all in a straight line in space. So here's just a cartoon illustrating the moon during new phase sometimes passes between the sun and the Earth, and the shadow of the moon is cast on the surface of the Earth, and the dark part, central part of the shadow, is where you have to be if you want to see the sun completely, the bright sun's disk completely blocked by the moon. So it's called the umbra, and it's a narrow path about 100 kilometers across on average during a total eclipse. And if you're within this lighter colored, or this lighter circle that you see on the diagram on the Earth, it's called the penumbra, then you only see a partial eclipse. And it's quite different than the experience of a total eclipse. The sky is still bright. You don't see the faint atmosphere around the sun called the corona that was visible here on this photograph. So these faint streamers in the outer part of the sun's atmosphere is called the corona, and we can see that during a total eclipse, but you don't see it during partial solar eclipses. And so I call these perfect eclipses because of the very close match in angular size on the sky between the sun and the moon. And people have noticed this for centuries and just said, wow, that's an interesting coincidence. But they had no explanation for it. Have you ever noticed when the sun is rising or setting and you can see it on the horizon as a red ball, and then looked at the moon rise, say a full moon rising? Have you noticed that they're very close in size on the sky? They're about a half a degree, 1/2 degree, almost the same on average. And it seems that there shouldn't be any reason why they should be. And that's why so many people have wondered about this interesting coincidence. But I think I have a good answer to that, which I'll try to present in the next few slides. But first, one of the things I explored in my 1999 paper in Astronomy and Geophysics was just comparing this size ratio between the angular size of the sun and the angular size of the moon in our sky to what the other moons would look like from their host planets in the solar system. And so the horizontal axis here at the bottom is the angular size ratio. So in a logarithmic scale, as you can see there. So the angular size of the satellite or moon compared to the sun as viewed from the surface of that planet. So 1.0 would be a perfect match. And these are dashes because of the sometimes elliptical orbit of the moon in combination with whatever ellipticity the planet's orbit has. So those are combined, and that's why there are dashes here. And you can see that the Earth's moon cuts this dashed line, dotted line here, almost perfectly down the middle. So just, it's a different way of stating what I already said, that the match between the sun and the moon on our sky is almost exact. That's why I call it a perfect eclipse. Now, notice that the Earth is the first planet shown here at the top. There are a couple of other planets, Mercury and Venus, that I don't have here. And the reason I don't have them on this plot is because they don't have moons. So Earth is the closest planet to the sun with a moon, which means Earth's eclipses are going to give you the largest angular size of the eclipsed sun on the sky of any planet in the solar system, because by virtue of the fact that it is the closest planet to the sun with a moon. Mars has 2 very small moons that orbit close to the surface of Mars, but they're still not close enough to cover the sun. So they're on the left side of the dotted vertical line. And then you can see the moon, some of the larger moons of Jupiter, Saturn, Uranus, Neptune, and I even included Pluto. When I made this plot, Pluto was still called a planet, by the way, which is why I have it on this plot. But there's another moon here that does cut that vertical dotted line, and that's Prometheus around Saturn. Prometheus is one of these shepherd moons. It's in the ring system. It's on the edge of the ring system. And it's a small potato-shaped moon. It's potato-shaped because it's too small for its gravity to make it into a sphere. And so it doesn't have this nice circular shape that our moon has on the sky. And it whips around Saturn really fast by virtue of the fact that it orbits relatively close to the planet, and it's orbiting a much, much more massive planet than the Earth is. So its eclipses would last only about a second or so. This is another aspect of this Earth's eclipses that it was really quite a bit better than other eclipses. And a reason I call them perfect solar eclipses, because they're longer duration. See, the moon orbits a relatively low mass planet. And so, and it orbits relatively far from the Earth. So eclipses last a long time, up to 7.5 minutes for a total eclipse. Whereas moons orbiting around these giant planets whip around those planets fast because they're orbiting around much more massive planets. And so because of the stronger gravity, they have to orbit around faster. And so multiple reasons why we have the best eclipses in the solar system. And so now I want to make that connection between eclipses, solar eclipses, and the habitability of a planet. Why is it that we're the only habitable planet in the solar system? And it's also the best place to view solar eclipses from. Is it just a coincidence, or is there some deeper connection? Well, you might, first of all, let me say as an aside, you might say that by itself, the fact that we have the best eclipses in the solar system, just from this simple comparison, that I think that could form a weak kind of design argument, just by itself, just that simple observation. But I think you can make it much stronger by noting the following length. Remember, I talked about circumstellar habitable zone. The planet needs to be within the circumstellar habitable zone around its host star, so it can have liquid water on the surface of its planet. Well, that's a major habitability requirement. The Earth is within the circumstellar habitable zone of the sun. Now, so that requirement for complex life establishes what angular size any inhabitants on that planet will see for their sun. So the fact that we see the sun subtend a certain angular size on our sky is mostly determined by the fact that we have to be within the circumstellar habitable zone. So it's a requirement established by the laws of physics in this particular universe. So that's one half of it. Now, what about the other half, the moon? The moon, if you remember, I mentioned that a large moon stabilizes the tilts of the Earth's rotation axis. It also helps with the cycling of nutrients with the tides, and also provides some of the energy for the circulation of the oceans, the deep ocean currents, which also helps with climate. So the moon, the large moon, aids with habitability. It makes the Earth a more habitable planet. And so that's another part of the equation, right? So in terms of explaining why the angular size of the sun and the moon on the sky match, it's because, well, they match because the laws of physics are such that when you have a habitable planet for complex life, it's going to set the angular size of the sun in the sky, and it's going to approximately set the angular size of the moon on your sky. Now, I think you may actually even be more precise with the angular size of the moon with more recent research that I did not consider in the privileged planet, but more recent research seems to indicate that the mass of the moon is a very sensitive to whether or not it can support the stability of the Earth's rotation axis for an extended period of time. The moon, as it turns out, is just barely, almost too massive. If it were just a little tiny bit more massive, it would have resulted in a destabilization of the Earth's rotation axis. As it is, because it's just under this critical mass, it's been able to stabilize the tilt of the Earth's rotation axis for a large chunk of its history. So it looks like the laws of physics are set up such that the inhabitants of any complex, intelligent inhabitants of a habitable planet are more likely than not to enjoy total eclipses of the sun. So it seems to be baked into the laws of physics. Now, it didn't have to be this way. The laws of physics could have been otherwise. And it could have been a universe where the laws of physics were such that, well, no, the most habitable places are not the places that are best for viewing total solar eclipses. So this is in the sense that I mean that the conditions for life, the habitability conditions, correlate with the conditions for observability or discoverability. In this case, observing total eclipses of the sun. It's set up that way. So if there is intelligent life elsewhere on other planets, I think they are more likely than not to also enjoy total eclipses of the sun. Now it goes even deeper than that. Not only are they beautiful, wondrous things to observe, total eclipses of the sun are, but they have led to advancements in science. Many of you are probably aware of the fact that general relativity was proposed in 1915 by Einstein, and he proposed an observational test. And that test was conducted 4 years later in 1919 with a total solar eclipse by Arthur Eddington. And he confirmed Einstein's predictions, and it was done better in subsequent solar eclipses in years following that. And it led to the very rapid acceptance of general relativity, which was otherwise very controversial. But the fact that he made this, it was a risky thing to make this prediction, and it said, you can test my theory with this observation, and it passed. And so that was very convincing. And it turns out to be probably the most important theory in all of physics, is a general theory of relativity. And it's since been proven or confirmed with a number of other experiments, most recently in 1915 with the discovery of gravity waves for the first time. Helium, the second most abundant element in the universe, was discovered during a total eclipse of the sun in the late 1800s. And the observations conducted during solar eclipses, in particular with spectroscopy, has allowed us to reveal the physical nature of stars. We understood how the spectrum of the sun was produced, and therefore how the spectra of other stars are produced as a result of studying how the spectrum of the sun changes during the course of a total solar eclipse. So just a little cartoon illustration showing general relativity, that during a total eclipse of the sun is covered so you can see stars in the sky around the sun. You take photographs, and then you come back 6 months later and take a picture of that same part of the sky at night without the sun there, right? And you compare the photographs taken in the two cases, and they found that in the photographs taken during the total solar eclipse, the relative positions of the stars are different. They change. That's because the light of the stars that are near the limb of the sun on the sky has been bent by the gravity of the sun, because the gravity of the sun warps the space around it. That's what Einstein said it would do, and therefore change the relative positions of the stars. And that's the experiment that was done by Eddington in 1919, taking photographs of the sky around the sun during a total eclipse and measuring the positions of the stars. Okay, so I'm going to move on then to the next example of this correlation, and that's the galactic habitable zone. I just noticed this afternoon that the popular article that I wrote in Scientific American in October of 2001, it made the cover illustration. It's exactly 20 years ago. So this month is the 20th anniversary of this article, where I presented the popular version of our idea called the Galactic Habitable Zone that I co-wrote with Don Brownlee and Peter Ward from the University of Washington. But we also wrote a technical paper on it in journal Icarus. So I want to describe what that idea is. What is the Galactic Habitable Zone? So the idea is that on a galactic scale, there are two broad categories of phenomena that define the GHZ, or galactic habitable zone. One is the basic requirements for a habitable planet. Basically, what do you need to build a habitable planet, and in particular, a habitable planet within a habitable planetary system? So you need certain building blocks. You need certain elements and the right amount to build a habitable planet. And then the survival of complex life. Once you have your planet, make sure you're not going to have too frequent threats to life on that planet. So so what are the threats on the galactic scale to life on a habitable planet? So this is a very simple cartoon illustration of you might say a face-on view of the Milky Way. It's called a spiral galaxy because the spiral arms in the disk of the Milky Way form these spiral patterns. And the sun is located roughly halfway between the center and the visible edge of the Milky Way galaxy. And it's located between some major spiral arms, the Perseus and Sagittarius arms. There are some smaller arms that I don't have drawn on here that are kind of armlets. There are small arms that are located between major arms. They're less noticeable because they don't have as many of the tracers of the major arms, like massive blue stars, for example, and dust lanes. But the sun is located in a relatively quiet area, far from the busy galactic center and between spiral arms. Why is that important? Because one of the most significant threats to complex life in the galaxy are supernovae, exploding stars. And one of the most common type are massive star supernovae. And they are located predominantly along the spiral arms. And also they're more common towards the center of the galaxy, where the star density gets higher as you get closer. And they're less common towards the outer part of the galaxy. So if you want to avoid the threats from supernovae, you want to be far away from the galactic center, and you want to avoid the major spiral arms. Now, there's another aspect to this. By the way, this was my original illustration for Scientific American, but they didn't use it. They had an artist do the artwork for the article instead. But I have a skull and crossbones at the center here in the inner region of the galaxy, because not only the supernovae, but also there's a supermassive black hole at the center of the Milky Way galaxy, as is the case for other large galaxies we see around us. They seem to be ubiquitous. They have supermassive black holes in their nuclei. But from time to time, something gets too close to the black hole, gets ripped apart, forms an accretion disk, and emits lots of radiation. So right now, our black hole is in a dormant state, but it could turn on at any time if a star, for example, gets too close to gets ripped apart. So there are also supernovae that are more common towards the inner part of the galaxy. The star density is much higher towards the inner part of the galaxy, and it's much dustier. So there are a number of threats, like passing through a giant molecular cloud is also a threat. So it's generally much more dangerous the closer you get to the galactic center. Now, why is there this ring? Why can't you just say, well, what about the outer edge? Well, there's another trend in the Milky Way galaxy called the radiometallicity gradient. As you get farther from the galactic center, the abundance of heavy elements, or what astronomers call metals, declines as you get farther from the center. And so the problem is that you need metals, you need heavy elements like iron and oxygen and carbon and magnesium and silicon. You need these heavy elements to build planets, habitable planets. And if you don't have enough of these, then you're not going to have a sufficiently massive habitable planet. In particular, also the abundance of heavy elements is very important in making or creating Jupiters. Jupiters, as it turns out, the presence of Jupiter like planets around a star is very sensitive to the composition of the star. So if the star was born with relatively low abundance of heavy elements, it's very unlikely to be hosted by or to have a giant planet orbiting around it. And if you have more metals, then you're much more likely to have massive giant planets. So the architecture of a planetary system is very, very sensitive to the metallicity that the planetary system formed out of, what the metallicity of the cloud that it formed out of. And so that's why I have this outer edge to this annulus. If you get too far out, you're not going to have enough metals to make a habitable planetary system. And I think one can make a case that it's helpful to have a giant planet in a planetary system. It aids in its habitability. But if you have too massive a giant planet or too massive multiple giant planets, they can destabilize the system as well. I just have zoomed out here on the lower left, the circumstellar habitable zones, just showing you that they generally look similar, the galactic habitable zone compared to the circumstellar habitable zone. But that's just superficial appearance. It's very different reasons that they're defined by very different physical processes, even though they both look like annuli. So that's habitability for the Milky Way. But for scientific discovery, where would you want to be? Well, you want to be somewhere like the galactic habitable zone. You don't want to be in the very dusty, high density inner region of the galaxy. That would greatly inhibit your ability to do cosmology. In particular, you would have a hard time measuring the microwave background radiation, so-called. Microwave background radiation is what was discovered in 1964, predicted by cosmologists as a relic radiation left over from when the universe was a much hotter, much denser state. And it proved to be the clinching evidence for the Big Bang theory and evidence that the universe had a beginning. And today, it's measured with ever greater precision with probes that we put out into space. And astronomers spend a lot of money measuring it precisely because it's so information rich about the overall global properties of the universe. There's no other single entity that we can measure that tells us as much about the universe as the microwave background radiation. And our ability to be able to measure it will be greatly compromised if we were living in a dusty region of the Milky Way galaxy, like towards the galactic center, or within a spiral arm, which tend to be very dusty. We live in a pretty clear area between major spiral arms, far from the galactic center, great place to do cosmology from. In general, to do astronomy from, because we can still measure lots of nearby stars, because we are near in the midplane of the Milky Way galaxy in a very low dust environment. Could hardly ask for anything better. So what? What does all this mean? What does it imply? Well, I think it's confirmation of design. The correlation between habitability and discoverability or measurability is more likely on the hypothesis that the universe is designed for discovery than on the chance hypothesis. If you posit two competing hypotheses, that the universe is just the result of pure chance, no purpose, no design on the one hand, and then on the other hand, your hypothesis that the universe was designed for scientific discovery by its inhabitants. Well, this correlation is much more likely on the design hypothesis than it is on the chance hypothesis. So this evidence, I think, confirms design. So our modest conclusion is that the universe is fine-tuned so that environments habitable to observers will provide the best overall conditions for observation and discovery. In other words, science is baked into the universe itself, into its very properties from the beginning, the ability to do science. Science was meant to be something done by its inhabitants. So the universe is designed for discovery, is my basic conclusion. And with that, open it up for questions if there are any.
Okay, thank you so much,
Sure.
Dr. Gonzalez. And we have right now open for any live questions. Please speak up if you have one. Go ahead.
I have a question for Dr. Gonzalez. It's been said that on a clear sky, if you threw up a handful of sand, each grain of sand would represent every star that you could see in the observable sky. And yet, in terms of all the stars in the universes and the multiverses, that would be represented by every grain of sand on every beach in the earth. Does that make sense based on your perspective of the number of stars that are existing in the universe and universes?
Well, I haven't tried to estimate the number of stars compared to I know grains of sand. I've heard that then there are as many stars in the universe as there are grains of sand on the beach, or and a handful. I'm not sure which. I'm not sure which one fits. There are about 10 to the 22nd power stars in the observable universe. So I don't. Yeah, I think that would be a good exercise for somebody to try to verify how much sand you have to equate to that. But in terms of multiverses, you brought that up. First of all, we have no evidence for the actual existence of a multiverse for other universes. But my position is that even if there are other universes, that doesn't really bother me as far as evidence of design in the slightest, because that still doesn't remove the fact that we live in a universe that's designed for discovery specifically. It's in other words, it's not really an argument from probabilities. I'm not saying that we lived in a design universe because it's so improbable to have the Earth. My argument is that we see this peculiar pattern in our universe in which the best place for complex, intelligent creatures is also the best place to do science from and to discover the properties of the universe from. And so the fact that there might be other universes, so-called multiverses, does not remove that and doesn't affect it at all in the slightest. Now, if those other universes are also designed as well, if they were purposed, then maybe they also have this correlation within their universe because there was a designer who purposed them to be in that way, to have that correlation.
Let me just say, I'm not disputing your concept. I happen to be biased on your side as to the design.
Oh, I didn't interpret it to be that way.
I just wanted to say that the measurability component that you're talking about, habitability and measurability, is that the measurability could be far in excess of the numbers that even pull your conclusion as to the design, and which I agree with. You know, there's so many design comparabilities that you're talking about, like the Mandelbrot set of complex numbers, which is more mathematical than it is astrobiology or anything like that. But there is, I mean, I'm making the argument for design, I guess, but that was my question.
There's a book that might have the answer to that question about the grains of sand and the number of stars. There's a book called Counting to God. I think that's the title. That has a lot of these kinds of statistical and mathematical statistics in it. It might have that one in there, if I recall. I forget the name of the author, but I think it's called Counting to God.
Okay.
Look it up on Amazon.
Thank you.
Yeah.
Doctor, I have a quick question.
Yeah.
In regards to the arms in our Milky Way.
Yeah.
My understanding is the arms themselves are kind of like density waves.
Yes.
Perturbating through the galaxy. So not only are we the right distance from the sun, but we're also at the right timing, that we're
Yeah.
not in a high density part of the arm, which past or future we might be.
Right. There's research that's actually addressing that very question that a number of astrobiologists in particular have been addressing, is trying to figure out how often does the sun pass through the major arms of the Milky Way galaxy. And right now, that's still a research question that's unsettled. And it depends exactly, as you said, on the model that you take for the spiral arms. Is it a kind of static spiral arms within density wave that kind of rotate with a kind of like a rigid body, and then the stars orbit around as a kind of differential rotation, and there's a special place called the co-rotation radius, where the angular speed of orbiting star around the center of the galaxy is the same as the angular rotation speed of the spiral arm pattern. And if you're at the co-rotation or very close to co-rotation, then you're always going to be moving at the same rate as the spiral arms, and so you won't be crossing. If you're between them, then you'll stay between them. You won't be crossing them.
Wow.
And so that's certainly an active area of research within this question of habitability and the galactic scale. And that's one I didn't bring up. That's right. That could have a bearing on being at the right place in the Milky Way galaxy. There's still controversy as to where we are in relation to the co-rotation radius. And then the question of as to how frequently we would cross the arms. Yeah, I'd say that's an unsettled question, an active area of research, but it's a very interesting one. It's a dynamic question. But yeah, it's one that's worth watching in coming years to see if it's resolved.
Hey, Dr. Gonzalez, we have a question here in the chat room. It says, if you were writing the book now, is there anything you would add? So what research
Yeah.
are you doing now?
Yeah, good question. We actually published a new edition of the book, but the only change we made was to add a foreword. So it's a few pages long, and it's paperback. So it went from hardback to a paperback version. That was I think 2 years ago now. And so if the forward is then updating the reader as to what developments have transpired since 2004. And so I give a couple of teasers in there. I did find a new example of the correlation since 2004. And I wrote a research paper on it. It has to do with space travel. And I make the claim that the Earth is fine-tuned to optimize space exploration. So launching rockets and exploring the planets and even interstellar travel. So I make the case that the Earth is also designed for facilitating space exploration. And so the paper is in biocomplexity, I think it's called, if I remember now. But you can probably find a link to it at the Discovery Institute website. But I'm trying to remember the title. Solar system favored for space exploration or something like that. Can't remember now the title. But yeah, so we're hoping to come up with a new edition of the book for the 20th anniversary in 2024, but I don't know if I'm going to have the time to do the major update necessary to do that. So that's one new example that I have that I can share. And then there's also a geologist named Robert Hazen that we mentioned in the forward that has written on minerals. And he's made some pretty interesting statements about the great diversity of minerals that are found in the Earth's crust. And he makes the case that the Earth has an incredibly rich assortment of minerals, and he makes estimates of what the number of mineral species are on some of the other planets like Mars and Venus, and it's the Earth far surpasses. The Earth has something like 5,000 or so mineral species, and the number is only thought to be in the hundreds for Mars. And part of the main reason for this is because of its active geology and its active hydrological cycle, which helps to concentrate mineral species. Also, life has helped to concentrate and create various mineral species. And so that's another aspect that's nice to see, this confirmation, basically, because we discussed geology in one of the chapters in the original book. But it's nice to see Robert Hazen kind of confirming evidence of just how special the Earth and it's in providing the resources, the mineral resources we need for scientific discovery and modern technology in particular. So those are two examples I can give you.
Thank you, Dr. Gonzalez. We have another question on the chat room. What is the age of the Earth versus the age of the universe? Do you have any opinion on the age of human life on Earth?
Yeah, well, the age of the Earth is pretty well constrained now, mostly from primitive meteorites that went into forming the Earth, and also from the age of the sun, from models of the sun. You start with the current measured properties of the sun: its mass, its radius, its luminosity, its surface composition, and also its interior structure is derived from what's called helioseismology. So you start with those conditions, and you go back in time and you figure out how old the sun has to be in order to have those properties today. And that matches very well with the ages of these old primitive meteorites. And they both give an age about 4.6 billion years. And the fact that they both agree with each other, even though they come from very different directions, the age of the sun and the age of the oldest meteorites, gives you great confidence that you're probably getting the right answer. So the age of the Earth is about 4.6 billion years. Age of the universe, about 13.7 billion years, obtained from the microwave background radiation in combination with the expansion rate that we measure from galaxies. And then finally, the age of humans on Earth, that I don't know. I know there's cave art going back tens of thousands of years, and there's fossil bones that look like humans going back more than 100,000 years. So I don't know. It's somewhere in the range of tens of thousands of years, maybe even beyond 100,000 years. But that's not my area of specialty.
Hi, Dr. Gonzalez. I have a question on out of the parameters, all this measurement, or 9 different parameters that you mentioned, like perfect solar eclipse,
Yes.
Large layering processes, plate tectonics. You forgot about magnetic field.
Oh, yeah.
Of the Earth. And I also remember watching your DVD on the Privileged Planet. I think there was somebody there mentioned about each of these parameters has some big number, like 10 to the 20 chances of being perfect. So if you add all of them, multiply all of them together to have a perfectly habitable planet, it will amount to be a large number, like 10 to the 200 power.
Well, I don't. Yeah, I take a position. If you look at the video again, that we suppose that you give each of those. You have like 13 habitability requirements. Say each one is 10%. Now, it's kind of hypothetical because I don't really know the probabilities of those yet. A lot of those well enough to say it's this percentage or that percentage. So it was mostly like kind of a hypothetical discussion. And if you multiply those and assume they're all independent, it's 10%, 13 times. It's 10 to the 1 part in 10 to the 13th power. So there are about 10 to the 11th stars in the galaxy. So that's a 1% chance just for the Milky Way galaxy. But then there are lots of other galaxies. So, but there are other factors that I probably missed. I just picked 13. Excuse me. So my position is that I just don't know the probabilities well enough to say for sure that you exhaust probabilistic resources in the whole observable universe. Just for that's just for habitability. It's not talking about measurability yet. And so, but you know, if you look at the astrobiology research papers, almost every week there's some new discovery of some new constraint that was neglected previously for the habitability of a planet that somebody had overlooked. And so people keep finding new things that have to be just right for the Earth to be habitable. So yeah, I think the probabilities are getting smaller as astrobiologists research into this area. But I want to be very careful and not give any specific numbers just because I can't defend them yet. I haven't tried to pin down those numbers yet because I think a lot of them are still very fluid, and there's research being done, like I mentioned earlier, with the whether the sun is at or near the co-rotation radius of the galaxy. That one, has a potential for narrowing the galactic habitable zone even more, but we don't know. It's still controversial as to where exactly the co-rotation radius is and where we are in relation to it. And therefore, we can't yet establish how important that is for life in our solar system. But yeah, I think it's very exciting that there's so much research in astrobiology and they're discovering all these new conditions that have to go right. Yeah, the magnetic field, I do discuss that in the Privileged Planet. I didn't have time to discuss it in here in today's presentation, but the magnetic field is thought that it's quite closely connected to plate tectonics via the cooling that plate tectonics provides for the Earth's interior. It's a way of helping the energy to get out more quickly. And it's thought that this temperature gradient that it results in the Earth's interior makes it more likely to have the kind of circulation you need in the iron core to generate a magnetic field. When magnetic field is important for protecting life on the Earth's surface from charged particle radiation from space. So yeah, magnetic field is another one of those habitability requirements. But magnetic field turns out to be also very important in measurability. It's used like a kind of GPS to place the continents in Earth's past. So if you've ever seen these animations kind of showing how the continents have moved in the past, in Earth's past, and how there was a time when all the continents were kind of squeezed together and they started splitting apart. You may have wondered, how do they do that? Well, what they do mostly is they use ancient magnetism in ancient deposits on the Earth and measure the orientation of the ancient magnetic field. That's the fossil magnetic field in these rocks. And they're able to use that information to figure out where that continent was on the Earth, using the magnetic field as a kind of GPS system to figure out where the continents were in ancient times. I think that's just fascinating that the Earth has this magnetic field that geologists have learned to use to figure out how the continents were moving. And even today, right, you use a compass to figure out, at least north, to figure out a direction on the Earth's surface, just from the magnetic field of the Earth.
We have one question sort of along this line, and I think this question was posted prior to I asked that question.
Yeah.
If the size of the universe is infinite, does that blow away the habitability argument?
Right. So we don't know where the universe ends. Now, we know it's finite in age. I don't like to say infinite because infinite's such a tricky thing. A scientist can't talk about infinities because he's restricted to what he can observe. It would have to come from a theoretical argument of some sort. What we can talk about is, in observational astronomy, is how far back we can look. We can look back into the universe as far as light has been able to travel since the universe began 13.7 billion years ago. So over that time, the universe has been expanding, and so we have a certain look back time. And so the oldest light in the universe is the microwave background radiation, which goes back to nearly 13.7 billion years ago. But as far as, is there material things going out to potentially infinity? I would, I don't like to say there's an actual infinity. I got philosophical problems. I like to say what we know is what we can observe out to a certain distance, right? So there's the observational universe. I like to use that phrase, observational universe, or the observed universe, what we can actually observe and verify through observations. And that's really all we can say with certainty, is what we can see. But to say that the universe is infinite, it's going to require, and it contains matter out, potentially to infinity. As the universe gets older and older, the light gets farther and farther that we can see. We can see new objects appearing, maybe. I don't know. But I think that's a very hypothetical claim. And it's a difficult to defend one, that the universe is infinite. So as far as making mincemeat of the habitability argument, it would, if you can demonstrate the universe is infinite, because then you have infinite resources. And then so eventually, you have enough rolls of the dice that eventually you're going to get the Earth, and eventually you're going to get an infinite number of Earths, not just one or two. You're going to get an infinite number of them if the universe is infinite. But then that's kind of related to the question of multiverses. And do you have an infinite number of universes? I think there's a philosophical problem with advocating an infinite number of multiverses. It destroys a very possibility of doing science, because then nothing has an irrational explanation. It destroys the relationship of cause and effect, principle of sufficient reason. And so I think a designer could have created other universes. That's a different question. But as to whether there are infinite universes or if our universe is infinite, I think those are very difficult to prove questions, and they have philosophical issues. So I'll just leave. But of course, it doesn't touch the question of the evidence for design that I presented tonight. Even if the universe is infinite, it doesn't touch the evidence for design based on the correlation between habitability and measurability.
Yeah, my point when I raised that question about stars in the observable universe is just to suggest that there's a larger number of universes that would be the denominator that you would apply the habitability question to.
So yeah, I'll think of it in terms of probabilistic resources. If you have more stars, more galaxies, more planets, then you can think of it, each one as a roll of the dice, then chance has more room to operate if you have a bigger and bigger universe. In terms of trying to get at least one Earth, for example. We know there are other planets, and there are many other planets, many other stars, many other galaxies. And so the question is, how many of those do you need if you just think of them as different rolls of the dice in order to explain our one Earth?
I don't know if that takes away, it makes a bigger chance, because that's why I brought up the Mandelbrot set of mathematical formulas that can apply, order to any large number. So you could still have design, it just has a larger number to begin with.
Yeah, I would be careful with mathematical arguments, because the Mandelbrot set is what you might say is a logical necessity. The Mandelbrot set derives from a recursive algorithm in mathematics. And so it has to be, if you have the set of mathematical axioms and such, then that has to be the case. It could not have not been. In other words, it's a logical necessity.
Mhm.
And when you have a logical necessity, it's hard to argue for design. For example, if you look at the sequence of pi, and it's non-repeating, and sometimes the numbers in the pi constant are used as kind of random number generator. Would you expect to see a pattern in there that maybe is some hidden message? Well, I would say no, because pi is a logical necessity. It's the ratio between the circumference of a circle and its diameter, expressed as a fraction. But that's a logical necessity, so I don't think you can argue for design from that.
That's interesting. I would have thought you would have thought that the Mandelbrot set was more of an argument for design because of the design concept that those mathematical formulas take you to, at least from a visual standpoint.
Yeah, they can be very beautiful in the way they're constructed with algorithms. Now, there's an aspect of the algorithm that's human designed, and then choosing how to display the Mandelbrot set and then zooming in, if you've seen those movies. But the actual fundamental aspect of the Mandelbrot set derives from a recursive mathematical relationship and an algorithm on a computer, which is a logically necessary thing. In other words, it has to be that way. It's like 1 + 1 has to equal 2. It could not have been any other way. So I would be careful about arguing for evidence of design from mathematical axioms or algorithms. Now, on the other side of the coin, the universe seems to be very mathematical in its physical properties. There was a famous quote by a physicist about the unreasonable effectiveness of mathematics in the physical sciences, that it's remarkable just how mathematical the universe's laws are, and it just seems uncanny in that the universe operates. The laws of the universe seem to be very mathematical, like they're very mathematically simple, like the inverse square law for gravity. It's 1/r² to the second power exactly.
Yes.
Things like that. I think that's an interesting thing that's kind of surprising. And makes it easier to discover the physical laws, by the way, if they're simple like that, mathematical and simple. So I think there's an interesting aspect, having to do with mathematics in that sense, but not within a particular mathematical algorithm or axiom. I would say maybe in the applicability of mathematics to the natural world, like saying things like Mandelbrot sets in nature, like the recursive patterns we see in fern leaves, for example, the way they grow is very mathematical, or the structure of seeds in a sunflower is very mathematical.
Well, there's an existential question about mathematics. Which came first?
Yeah, and now you're getting into philosophy, which is outside my pay grade.
Mine too.
Yeah.
So there was let's follow up with this question. The word habitability is also we have to define, because you could have habitability for bacteria, viruses, or for intelligent life like us. Now, it's very easy to have a planet that's habitable for bacteria, but to get to a point of high intelligent like us, which is another very difficult obstacle to go through and highly improbable. Even now, the original life study has difficult time pin together how do we get to where we are, or animals get to where animals are today from the limited 4.6 billions of Earth life. And that's a big problem.
Yeah, and that's why I pointed out here that I was talking about complex life, and that's what I define habitability for. Because first of all, we're complex life, and so we're intelligent creatures, we're observers, And so the question of measurement and observability and discoverability really applies to complex life. And so it's more interesting to talk about complex life than it is to talk about, say, single-celled life. And certainly the habitable zone widths are broader for simple life like bacteria. It's quote simple life, not really simple, but single-celled life like bacteria, certainly. You're going to have a broader circumstellar habitable zone. You're going to have a broader galactic habitable zone because they can survive more harsh conditions than complex life, which requires very strict, actually, and narrow conditions in order to survive for a long time. Yeah, you're right.
We have one more question, actually, two more. Is non-carbon life possible?
I'm not going to say it's impossible, but I'm going to say, based on what we know from chemistry, which is a very well-developed science at this point, it's extremely unlikely, I think, that life is possible with anything other than carbon. That even, the closest thing to it that has been discussed in scientific and science fiction literature is silicon, right? Silicon-based life. But silicon still falls short of carbon and then this ability to form large metastable molecules. By metastable, again, I mean molecules that are stable enough that they're not going to fall apart with slight perturbations. And so they can transmit the information needed to make another copy of the organism, right? Because it lasts long enough. But it's not so stable that it's inert, like silicon oxygen bonds, for example, where you just, it forms materials that hardly react at all. And so, nobody's demonstrated in the laboratory, though they keep trying. And just look at the number of compounds that are based on carbon, the whole field of organic chemistry, compared to compounds based on any other single element in the periodic table. It's literally orders of magnitudes difference. Literally orders of magnitude. It's something like in the tens of millions, I forget what the latest estimate is, but maybe even 100 million different organic compounds. And the second best would maybe be somewhere in the hundreds for some other element, or maybe even thousands. But nothing comes close to carbon. And I recommend books written by Michael Denton on this topic of water and also carbon as being important, or I would even say necessary for life.
Thank you. How does the moon stabilize the Earth's rotation axis? My understanding is that the rotation axis will move over time and will not always point toward the North Star.
That's right. So in fact, the rotation axis does wobble, and but you have to be careful in separating two phenomena that may sound similar. One is called precession, and precession indeed is the direction in space that the Earth's rotation axis is pointed to, and it wobbles over a period of about 26,000 years. And that's right, the North Star is Polaris now, but when the pyramids were being built, it was a different star. In fact, one called Thuban. And at some other point in the future, it's going to be the star Vega. Now that's different. This wobble called precession is different from the tilt of the Earth's rotation axis, which is currently 23.5 degrees. So if you consider the Earth's orbit as defining a plane, the Earth's orbit around the sun is defining a plane, take the normal or perpendicular to that plane, and then go off 23.5 degrees from that normal, that's the tilt. So the tilt is 23.5 degrees, and that wobbles by about 1.5 plus or minus 1.5 degrees. So sometimes it's 22 degrees, sometimes it's 25 degrees. So that's what I mean by the tilt of the Earth's rotation axis. It's called the obliquity. That's the technical name for it. Is that 23.5 degree tilt? It's called the obliquity of the Earth's rotation axis, and that wobbles by just that tiny amount, plus or minus 1.5 degrees. If the moon weren't present, it would wobble by a larger angle. And why is that a big deal? Because even with this tiny wobble of 1.5 degrees, or on either side of 23.5, that leads to large climate changes. and those are known. They contributed to the ice ages, the cycle of ice ages over periods of thousands of years, and so that angle of wobble will be considerably greater if the moon weren't present.
Thank you. I think we'll make this one the last question.
Okay.
What do you think of the modern argument related to design in the free parameters in the standard model of particle physics?
In the free parameters of
Yes,
particle physics?
In the related to design in the free parameters in the standard model of particle physics.
So I'd say there's evidence of fine tuning in the free parameters, like the masses of the fundamental particles, the relative masses of the quarks, of the electron, the Higgs energy, and there was something else. There's a paper written by, I'm trying to remember his name, a physicist at Delaware. Ancient Physics, Modern Faith is a book he wrote, and he discusses that fine tuning of the fundamental particles. Also a book written by, I can't remember, I'm going blank on names tonight for some reason. Yeah, I'm remembering his name. It's a recent book written on the fine tuning of the universe by an Australian cosmologist. If everybody remembers his name, I'm going blank right now.
Was it Luke Barnes and
Luke
Geraint
Barnes,
Lewis?
that's it. Thank you. Luke Barnes and Geraint Lewis. Yeah. About fine tuning in the universe. And they have a detailed discussion about what would happen if you change the relative masses of the quarks. For example, how would it affect the protons and neutron properties? And then how would that affect matter in the universe, the stability of matter, or the ability to form anything more complex than hydrogen, for example. There are lots of dramatic repercussions if you just change the relative masses. Also, the relative strengths of the fundamental forces of nature. So there are 4 fundamental forces. If you change the relative strengths, that would lead to dramatic effects. And fine tuning, and for example, just gravity, the relative strength of gravity compared to the others, just one part in like 10 to the 39th power, or something like that. It's a really high degree of fine tuning. So the fine tuning, I would say, is the most impressive aspect of particle physics.
Okay, do we, I guess that was our last question.
All right.
Thank you so much, Dr. Gonzalez.
Sure.
I think you definitely show us that the probability of a design is very high. And the more we know in science, especially the last few years, the more the confirmation of there's a design.
Yes, absolutely.
God, yeah. So if there's no other question, I think we can just conclude this presentation, and we want to thank Dr. Gonzalez for coming to talk to us, and it's our privilege to have you.
Thank you.
When we invite you again in the future sometime.
I enjoyed it. Thank you. Sure.
Okay.
All right. Good night.
Okay. Thank you. Good night.
Bye.
Bye-bye, everyone.
Good night.
Good night. Thank you.